So in different states, there are particles and they can be distributed in different ways. Okay. So in general, the number of states are very large and there will be continuous change in their number in passing from one region of the phase space to the other. The state of the system is going to change. Because of that, the distribution of particles in a system are also going to change. ಯಾವ ಸ್ಟೇಟ್ ಅಲ್ಲಿ ಯಾವ ಪಾರ್ಟಿಕಲ್ ಇದೆ ಅನ್ನೋದನ್ನು ಹೇಳುವಂತದ್ದು distribution function. So this can be described by statistical function called distribution function. ಅದಕ್ಕೆ ನಾವು distribution function ಅಂತ ಕರಿತೀವಿ. What is the definition of distribution function? The condition described by a function according to which the phase points of the ensemble are distributed in a phase space is called distribution function. So how does the particles are distributed in a phase space is called as the distribution function. So it explains the way of distributing the particles. A simple example is the distribution of electrons in an atom. There are certain rules. Electrons so electrons can be found in different shells. First shell, second shell, in the S shell, 2 electrons are there. In the P shell, 6 electrons are there. You have to consider the Pauli's exclusion principle. So different things you have to consider to understand the distribution of electrons. That is one distribution function. Okay, adana explain maduvanthadu distribution function. Okay, so just to remember, distribution function is the equation which gives the explanation of distribution of particles in a particular system. Okay, that is called as distribution function. Next, in phase space, the distribution functions are functions of position and momentum coordinates, and that is given by f equal to, which is a function of xyz and px, py, pz. Okay, so that is a function of position and momentum coordinate. Then the number of particles in a particular phase cell is given by this expression. I think I have given you the explanation of this expression in the previous class, where this product is actually volume of the phase cell. That is smallest unit in the phase space. So dx, dy, dz and dpx into dpy into dpz gives the volume of the phase cell. In that volume, how many number of particles are occupied? That is given by this equation, where dn represents the number of particles occupied in this particular volume. ಈ ವಾಲ್ಯೂಮ್ ಅಲ್ಲಿ ಎಷ್ಟು ಪಾರ್ಟಿಕಲ್ ಆಕ್ಯುಪೈ ಆಗಿದೆ ಅನ್ನೋದನ್ನ this equation is explaining. Okay, next. So finally, what it represents, distribution function explains the distribution of phase points in the phase cells. Phase points andrenu, it is a state of the system. So it explains the state of the system in phase space. That is known as distribution function. Okay, ಯಾವ ತರ ಪಾರ್ಟಿಕಲ್ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟ್ ಆಗಿದೆ ಅನ್ನೋದನ್ನ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡೋದು distribution function. So there are 3 types, except those things we'll study in the upcoming classes. So how this distribution function can be expressed in terms of the function of energy? So distribution function can also be represented as a function of energy, because energy is a function of momentum and position. We know that kinetic energy is depending on the momentum of the particle, where potential energy is the energy due to its position. So momentum and position coordinates are used to represent the state of the system in phase space. You can express this momentum and position in terms of kinetic energy and potential energy. The sum of these two energies is called as total energy. So basically, the number of particles or phase points having energy E is given by this expression, where n of E represents the number of particles having energy E, which is equal to the distribution function f of E. So this is the distribution function, which is a function of energy, and G of E is called as density of states, or number of available states with energy E, because our state only particles distribute ಆಗಬೇಕು, and that distribution should be accordance with f of e, and that will give you total number of particles present in that particular energy E. Energy E ಅಂತ ಒಂದು ಸ್ಟೇಟ್ ಇದ್ರೆ, in that state how many particles are occupied? For a simple example, I will give the electron distribution in hydrogen atom. Sorry, helium atom you can take. Helium atom ಅಲ್ಲಿ 2 electrons ಇರ್ತದೆ, 2 electrons are there. Those 2 electrons should be placed in S subshell. Energy of these 2 electrons should be same, but spin of the electron should be opposite. One is plus half spin, another one is minus half spin. So that is how in that state, in that particular energy state, high energy level ಅಲ್ಲಿ 2 state available ಇದೆ. One state is up spin, another state is down spin. Only 2 particles are allowed. That is actually number of states allowed. F of E is the distribution function, and these electrons are distributed according with Fermi-Dirac distribution function. Okay, and if you multiply that distribution function into number of allowed states, that will give you total number of particles present in that energy state. So this is the example. So just to remember, always this equation is true. If you want to find out a number of particles in a energy state E, then you have to take the product of distribution function and density of states or number of available states. Okay, so the distribution function gives the average number of phase points in each state of energy E, or the probability of finding the states with energy E. ಎಷ್ಟು particle ಇದೆ ಅನ್ನೋದನ್ನು ಕೊಡ್ತದೆ. It also gives you the probability. Okay, so basically distribution function is given by n of E divided by g of E, number of particles present So number of particles present in state E divided by the density of states G of E. Suppose we have the smallest part of the energy space. Okay, under DE, if you divide the phase space into small number of elements, each of energy D of BE, then how this number of particles are represented? That is represented by this equation. Just you have to multiply the smallest volume element. This is volume of the smallest phase cell in the phase space. N of E into DE equal to F of E into G of E into D, where G of E into DE is called as number of states with energies lying between E and E plus D. Okay, when you D in the multiply madidre, this will give you number of particles present in having the energy between E and E plus D. Okay, so just you remember, so this is how we can express the number of particles in a state in a given system in terms of distribution function and density of states. Okay, this product ನೀವು ತಗೊಂಡ್ರೆ number of particles ಸಿಗ್ತದೆ ಅಂತ ನೆನಪಿಡಬೇಕು. Okay, next we will try to derive the expression for density of states G of E. So in phase space of the system with F degrees of freedom, the volume of the phase cell is given by this dq1, dq2, dq3, so on up to dqf into dp1, dp2, dp3, so on up to dpf. Because there are f degrees of freedom, we need f position coordinates and f momentum coordinate. Totally you need 2f number of coordinates to describe the system. So if you take a smallest element in the phase space, that will be given by dq1, dq2, dq3 into dqf, so on up to dqf, into dp1 into dp2, dp3, so on up to dpf. You have to take a smallest element of q1, q2, so on up to qf, and multiplied by the smallest momentum. Okay, smaller momentum in that particular phase space. So that is giving you the volume of the phase cell in the particular phase space considered. Okay, it has f degrees of freedom. That's why you will have f number of position coordinate into f number of momentum coordinate. Therefore, what is the total volume of the phase space then? Okay, occupying the system. So this is volume of the phase cell. ನೀವು ಅದನ್ನ integrate ಮಾಡಿದ್ರೆ you will get a total volume. ಈಗ ಫೇಸ್ ಸ್ಪೇಸ್ ಅಂದ್ರೆ ಏನು? ಇಟ್ ಈಸ್ ಕನ್ಸಿಸ್ಟಿಂಗ್ ಆಫ್ ಲಾರ್ಜ್ ನಂಬರ್ ಆಫ್ ಫೇಸ್ ಸೆಲ್ಸ್. ಅದರೊಳಗೆ ಸಣ್ಣ 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 ಫೇಸ್ ಸೆಲ್ಸ್ ಇರ್ತವೆ. ಈಚ್ ಫೇಸ್ ಸೆಲ್ ಇಸ್ ಹ್ಯಾವಿಂಗ್ ದಿಸ್ ಪರ್ಟಿಕ್ಯುಲರ್ ವಾಲ್ಯೂಮ್. ಈ ವಾಲ್ಯೂಮ್ ಇದೆ ಅದಕ್ಕೆ. ಇಫ್ ಯು ಇಂಟಿಗ್ರೇಟ್ ದಿಸ್ ಇಕ್ವೇಶನ್ over minus infinity to plus infinity, that will give you the total volume of the phase space, or total volume of the phase space which is occupying the system. Total volume of the phase space you will get. Okay, so once you do that, what is this dq into dp? So you take 1 dq1 into dp1. Basically dq is position coordinate, dp is momentum coordinate, which is having the dimension of angular momentum, because position into momentum is angular momentum. And for the system with f degrees of freedom, the dimension of the integrand of above equation will be dq into dp to the power f. ಎಷ್ಟು dimension ಬರ್ತದೆ ಇದಕ್ಕೆ? So if you take dq1 into dp1, dq2 into dp2, dq3 into dp3, like that, if you take, you will get the total dimension of this equation. So you have to integrate this dq into dp to the power f times. ಇದು dq1 first integration, dq2 with respect to q2 ಮಾಡಬೇಕು, with respect to q3. So finally you will get total dimension of the integrand. This particular one will be dq into dp to the power f, because there are f number of position coordinate, f number of momentum coordinates. ಇದು product ತಗೊಂಡ್ರೆ ಅಂದ್ರೆ dimension will be dq into dp to the power f. Okay, so let us take this dq into dp as h, which is a constant with the dimension of angular momentum, because we have face cell is having constant dimension because all are identical. Okay, ಎಲ್ಲದು identical ಇರೋದ್ರಿಂದ ಅದರ length, breadth, width ಆ ತರ ಎಲ್ಲ dimension is same ಇದೆ. That's why in general I will take this dq into dp as h, which is a constant, which is having the dimension of angular momentum. Now you substitute here, you take volume of the each phase cell. ಈಗ ಪ್ರತಿಯೊಂದು phase cell ನೀವು ತಗೊಂಡ್ರೆ ಅಂದ್ರೆ that will have the volume h to the power f. Okay, so ಇದನ್ನ ಏನು ಎಕ್ಸ್ಪ್ರೆಸ್ ಮಾಡ್ತಾರೆ? I will express this as h to the power f. What is h here? H is the dimension of smallest phase point, dq1 into dp1, ಅದು h to the power f. If each phase cell is considered as a single state, then number of state of the system is given by density of state G is equal to volume of the phase space divided by volume of the phase cell. Okay, total volume divided by volume of one cell, that will give you total number of available states. ಎಷ್ಟು states occupy ಆಗಿದೆ ಅಂತ ಕೊಡ್ತೀನಿ ನಿಮಗೆ. So that is given by V divided by h to the power f, where V is the total volume divided by volume of one cell, that is h to the power f, where h is a constant which is having the dimension of angular momentum. Okay, remember that. Next, so that is how you can understand the density of states. Density of state is given by total volume divided by volume of the single phase cell. Then if phase space is represented in three-dimensional momentum space, okay, so all momentum are considered, no position, only momentums are considered, then how to represent that? That volume enclosed by two concentric spheres of radius p and p plus dp is given by 4 pi p square into dp. So phase cell in momentum space is represented as a sphere. Sphere ತರ represent ಮಾಡ್ತಾರೆ ಅದನ್ನು. Okay, so that sphere is having, the outer sphere is having the radius p. So outer sphere is having the radius p, inner sphere is having the radius p plus dp. Then what is the volume of that strip? That is given by 4 pi p square into dp, where 4 pi p square is surface area of that sphere into the thickness of the sphere dp. Okay, the number of states for particles with coordinates lying between p and p plus dp is given by this expression, where g of p into dp gives the density of states equal to total volume by h cube into 4 pi p square into dp. So it is a three-dimensional space. I have taken three-dimensional space. That's why degrees of freedom f will be 3. That's why h to the power f ಅನ್ನೋದು ಏನಾಗ್ತದೆ h cube ಆಗ್ತದೆ into the volume of that particular sphere, that is 4 pi p square into dp. Okay, that is how you can represent density of state in terms of momentum coordinate only. Idu in terms of position coordinate, general expression, v by h to the power f, general expression, where f is the degrees of freedom, v is the total volume, h is the angular momentum coordinate. Okay, that is p into q. In momentum space, ಅದರಲ್ಲಿ ಈ ತರ ಬರ್ತದೆ equation. You ನೆನಪಿಟ್ಟುಕೊಂಡ್ರೆ ಅಷ್ಟೇ, they are not much important in the examination point of view, but you remember this. In terms of energy space, energy ಎಲ್ಲ ಯಾವ ತರ ನೀವು ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಬೇಕು? So just you substitute p square equal to 2me. So how to represent kinetic energy? E is represented by p square by 2m. Therefore you will put p square equal to 2me. ಈ equation ಅಲ್ಲಿ p square ಇದ್ದಲ್ಲಿ ಏನಾಗ್ತದೆ ನೀವು 2me ಅಂತ ಹಾಕಿ, dp ಇದ್ದಲ್ಲಿ in terms of, so ಇದನ್ನು ನೀವು ಡಿಫರೆನ್ಸಿಯೇಷನ್ ಮಾಡಿದ್ರೆ you will get 2p dp equal to 2m de ಆಗ್ತದೆ. 2p dp equal to 2m de. So dp will be equal to m de by 2p ಆಯ್ತು. What is p? P is square root of 2me. So p is square root of 2me. Okay, so dp will be 2 gets cancelled here, m de divided by square root of 2me. ಅದನ್ನ ಇಲ್ಲಿ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡ್ರಿ. For p square you substitute 2me, for dp you substitute m de by square root of 2me, and then simplify it. You will get g of e into d will be equal to 4 pi mv divided by h cube into 2me to the power half into d. So the term g of e gives the number of states per unit energy. Okay, range around energy E, and is known as density of state in terms of energy density of states in terms of the energy space. Okay, momentum space ಅಲ್ಲಿ ಯಾವ ತರ ಬರ್ತದೆ ಅದು ಗೊತ್ತಿರಬೇಕು. Okay, so this is the density of states. Next, we'll take Stirling approximation. This is important because you have to understand this properly. What this Stirling approximation says, it is an analytical approximation for factorial of very large number, and it runs as ln of n factorial equal to n ln of n minus n. That is the Stirling approximation, and this applicable where n is very large. ಈ formula ಯಾವಾಗ apply ಆಗ್ತದೆ? When n is very large. When it is more than 1000 or more than 2000, then this formula holds very good. So this is an analytical approximation for the logarithm of the factorial. Ln means what? Ln is actually log to the base e. Log to the base e of factorial n will be equal to simply n ln n minus n. Okay, that formula you have to remember. So simple proof is there. Let us consider the proof of this Stirling approximation. So proof, we have n factorial. What do you mean by n factorial? N factorial is product of all integers up to n. So that is 1 into 2 into 3 so on up to n minus 2 into n minus 1 into n. So you have to take all the integers and take the product of them. So if you take log on both sides, take log to the base e on both sides, you will get a log to the base e, that is ln of n factorial will be equal to ln of 1 into 2 into 3 so on up to n. What is this ln of 1, 2, 3, 1 into 2 into 3? That is given by ln of 1 plus ln of 2 plus ln of 3, like that. According to logarithmic equation, you will get ln of n factorial will be equal to ln of 1 plus ln of 2 plus ln of 3 so on up to ln of n. Okay, so ln means 10 to the, log to the base e. Okay, so this is actually summation. This can be represented as summation of ln n, where n runs from 1 to n. Okay, it runs from 1 to n. It is a integer summation where ln of n has to be taken. Ln of 1 plus ln of 2. Summation of ln of 1, where n takes the values from 1 to n. Next, this summation can be represented as integration. Okay, as a series is continuous and term values are very small. So this series is continuous and there are large number of terms are there. That's why I can write that summation as integration, because integration is also summation over certain range. That's why summation can be represented as an integration, that is integration of ln n with respect to n, where integration runs from 1 to n. Okay, so now integrate this and try to get the right hand side. Left hand side is ln of n factorial, try to get the right hand side. So I can write this equation as ln of n into 1, because in order to do the integration by parts, you know that integration of log of x, what is again? By taking the integration by parts, you have to take multiplication by 1. 1 iddange you consider madkondu, you take this as first function, take this as second function. Okay, so that is integration by parts. So that is given by first function into integral of the second, integral of 1, integration of 1 is n. Okay, minus integration of derivative of the first. What is the derivative of ln of n? Differentiation of log of x is 1 by n. So derivative of ln of n is 1 by n into integral of the first. So integral of the second. Integral of the second is integration of 1 is n. Okay, so lower limits is 1, upper limit is n. Simplify this. Isn't a simplify matter. If you simplify this, ln of n into n, first term, minus ln of 1 is 0. Ln of 1 is 0, so second term becomes 0 here. Minus integration of this n gets cancelled, you will get integration of dn. So upper limit is n, lower limit is 1. So you will get n minus 1. Either integration ಮಾಡಿ lower limit ಮತ್ತು upper limit substitute ಮಾಡಿದ್ರೆ you will get n minus 1. Then you simplify it further, you will get n ln n minus n plus 1 you will get. So compared to value of n is very large. Compared to value of n, 1 is very small. Since n is very, very large, greater than 1, therefore I can neglect this 1. Therefore, that's why it's an approximation. So approximately ln of n factorial is equal to n ln n minus n. So this is called as Stirling approximation. This is useful while studying the distribution function. Distribution function derivation ಮಾಡಬೇಕಾದ್ರೆ this Stirling approximation is much necessary. Okay, so this is known as Stirling formula or Stirling approximation. It is very important in statistical mechanics that deals with very large number of microstates. So somewhere you will get a ln of n factorial. In order to simplify that distribution function, you need this Stirling approximation. Okay, so this is what you remember. So this thing we'll consider in the next class, relation between entropy and probability. Then the next class ivattu complete madlikagalla. This is having little bit longer lengthy derivation. So today we have considered the density of states. Density of state discuss ಮಾಡಿದ್ವಿ. So here density of state is given by volume of phase space divided by volume of the phase cell. So volume of phase space is V and volume of phase cell is H to the power F, and we have represented density of state in terms of momentum, then density of state in terms of energy, and finally we have done the Stirling approximation derivation. This is very simple. Okay. So I will share the notes.